So we'll simply go back to chemical reaction kinetics. We have a state A and a state B. We know that there is a reaction Ka to B, and there is another reaction Kb to A. We also know that the chemical equilibrium constant, uppercase K, the ratio of B to A, that's going to be, again, at the equilibrium, the number of molecules going from A to B divided by the rate going from B to A. And another way of writing that is going to be at equilibrium, that's going to be the number of molecules in state B divided by the number of molecules in state A. What I want to know now is that how does something, let's focus on state A for instance, how does the number of molecules in state A, the derivative, change as a function of time? Well, there's going to be the flux away from state A, that's the number of molecules per second multiplied by the density. Leave some space there. So that's going to be proportional to the number of molecules A at that time, and then things are moving away, so it's a minus sign, and that's K from A to B, right? But I'm also gaining molecules. I'm gaining the molecules going from B to A multiplied by the current concentration in state B. There are a few too many variables here. So we can introduce that N0 is always equal Na plus Nb. That's particularly going to be true at infinity, but N0 does not change. And that means that I can write this Nb as N0 minus Na. And that means that this becomes Ka to B, leave some space, Nat, plus Kb to A, N0 minus Na, multiplied by Kb to, there is already a minus sign there, so I can say Kb there, B to A there. Already here, in principle, we have the results. The derivative here is now going to be, the change here is going to be proportional to the current concentration in state A, but you see here that we have the sum of the two reaction rates, which initially looks really strange, but it's not that stupid. If we're thinking about the rate at which I approach equilibrium, things moving from the left to right and right to left, they're both going to help me equilibrate, right? So that the total apparent rate with which the reaction appears to happen is actually the sum of both rates. Very surprising. We can do this slightly more formally and solve the entire partial differential equation, but it's not really that important, so I'm not going to do it. The book does it if you want to follow it. But the idea is that we have an apparent rate Kap, which is equal K from A to B plus Kb to A. In practice, this is much easier to measure in the lab because I don't have to worry about molecules going in the wrong direction. This is just everything. Just measure how fast the reaction happens. I don't care in which direction it happens. We're going to need a different plot to plot that in. It's called the chevron plot, and let me show you what it looks like.